Okay, hello. I know it's been a minute since I made any video. I've just been kind of struggling with a few things. Some of it's some of it's a product rule or not product rule. Some of it's this rule I'm about to show you, and some of it's just other stuff I'm doing. Um, but anyways, this is called the chain rule, and the chain rule is where you're trying to take the derivative of composites. And composites, if you remember, you can denote it a few ways. You can say FOG, you could say F of G of X. You can write it like that. If we're writing it as an example, though, if I were to say, I don't know, 4x squared plus 3x plus 2 to the fifth power, and you want to take the derivative of this, it's not very straightforward. If you want to, you can expand this out to your heart's content. I'm personally not very inclined to do so, because I mean, if you went through that, then you could use the sum rule combined with a bunch of other rules and take the derivative. But that is just way too tedious and unnecessary, and there's a much easier way to do it. Um, that being said, you cannot just expand something like sine of 3x. How are you going to expand that, right? The derivative of sine is cosine, but the derivative of sine of 3x is not cosine of 3x. I'll just let you know. So it's not that easy. But luckily, the chain rule is a very, very short, concise, and once you get to know it and understand it, it makes sense. Uh, Unfortunately, I couldn't really find a lot of good videos on it on YouTube. Not the best explanations. I know there are some out there, but they don't really. I just don't think they explained it the best way. They just kind of they kind of more just give it to you and expect you to use it without understanding it. And I think it's better to understand it first and then use it. They usually do it the other way around, which kind of makes it weird. But here is the chain rule. The chain rule is, well, it's kind of hard to write without. Okay. I'll just go ahead and prove it first. I think that makes more sense. So the chain rule is, let's say we have a function. I'm just going to write an example here. Let's say we have 4x plus 3 to the seventh power. Okay. Now I can write this in composites. I can say u to the seventh. I can say this is equal to y, and I can say u is equal to 4x plus 3, right? I'm just kind of breaking this function into pieces, right? U is equal to this, so I could plug this back in whenever I want. But breaking it up like this, I think, is a very good, important step, or at least you need to conceptually understand it in your head what you're doing, because this is like a key point, right? So I like to start solving these problems by just breaking them apart, either in my head or just at least having in the back of my mind. So for proof, though, it's important to break them apart. So if we break them apart like this, and I want to just generally say the change in u. Now the change in u, I'm going to write what is the change in u equal to. Now in this case, it's going to be something else, but I'm going to write it in a generalized term to where it's applicable for anything. And I'm going to say it is going to be g of x. Notice I'm using x here because it is with respect to the variable x here. Minus g of x. And you'll notice this is this is just the change in u. You have some value of u minus another value of u, and you get your change in your u. Okay, now our change in our y is going to be, let's say, f of u plus change in u minus f of u. Okay, and notice I'm using u here because that's what this function involves. Okay, so if I want to find the rate of change here, which is an important step for derivatives. If I want to find the rate of change of u here, I know it's going to be delta u over delta x, right? That's what our function is with respect to. That is our variable. Okay, so if I want to find the rate of change, find the slope of that function, it'd be this. If I want to find the slope of this function, it would be the change in y over the change in u, because in this case, we're paying respect to u. Okay, now for our function, when we're taking derivatives, we're typically doing change in y with respect to x, right? We're finding what we want ideally is a change in y over a change in x, because that's what kind of kicks us off with our derivatives, right? That's your general slope. And you can get this by just multiplying these two together. And you'll notice that these cancel. And this, you'll be left with delta y over delta x. Now, if I want to take the derivative of this, it would be the limit as delta x approaches 0 of delta y. And this is exactly what we expected in our composite, right? That's what the derivative is. This is exactly what you would expect. Okay. And this would be the derivative of y. It'd be y prime, f prime of x, whatever you want to denote it as, d over dx of y, dy over dx, whatever. Okay. So if I'm writing it like this essentially does absolutely nothing for me, because like we said, it's not going to work just like that. I can't just plug in these two values and differentiate it like that. So we have to break it back into these two pieces, but keep this in the back of your mind. So just keep remembering that that's what those are equal to. So if this is equal to these two multiplied together, then I can just rewrite this as the limit, since these are equal, as delta x is approaching 0. And I'll say delta u over delta x. Actually, I'm going to write it the other way because that's how it's usually written. I just kind of wrote it backwards. I'm going to say delta y over delta u multiplied by delta u over delta x. Okay. Remember these, it's just the same thing. I just wrote it in a different way. Okay. Now, for this one here, you'll notice that this is just going to be the derivative of u with respect to x. But that doesn't work for this one. And I'll show you a way around that in a moment. But just so you know, it is a limit rule, a limit property, that you can split this into two limits here. So I'm going to write this first one as the limit as delta u, and I'll explain that in a moment, as delta u is approaching 0 of delta y over delta u. And then multiplied by the limit, another limit, as delta x, this is just a limit property, as it approaches 0 of delta u over delta x. Okay, now this first one here, we know is going to be equal to just du over dx, right? Now this other one, we also know is going to be equal to, I can't draw. Okay, we know this other one is going to be equal to dy over du. Okay, but why are we able to just say delta u can approach 0, right? That's not what the limit originally was. It was delta x approaching 0. We can't just say that and make it true, because it's, it is, but we can't just say it with no reason. And what I want you to do is think of it like this. If we have delta x approaching 0, and we're looking at our change in u here, if we're looking at what delta u is equal to, if delta u is equal to g of x plus delta x minus g of x, then as delta x is approaching 0, like we originally said over here, as it's approaching 0, then delta u is also approaching 0. So I can substitute that in. Okay, so right? Like if you think of it like this, if this is 0, it doesn't necessarily have to be, but as it tends towards 0, we're going to be essentially just getting g of x minus g of x, which is 0, right? So we can just say as delta x is approaching 0, delta u is approaching 0. Same thing. All right, so that's how we're able to do that. So then we'll have dy over du times du over dx. And that is the chain rule. So that was kind of a mouthful. Hopefully that makes sense. I'm just going to go ahead and employ that here with an example. I'm going to move, let's use our original example here. I'm going to try and save space here because I don't have any room. Okay, I'm going to move this, give myself, I'll just get that out of the way. Okay. Kind of make a little working section. Okay. So in this case, we know that we have a formula down here, dy over du times du over dx. And I've already broken these into two composites, or two functions themselves, which is a composite in itself. So our first step is going to be taking the derivative of this, which, as you might notice, is dy over du. It's our change in y with respect to u, not x, because there's no x in this situation. So I'm going to write it. If you notice, this looks awfully familiar to x to some power, and it works the exact same. I'm just saying that it's the same thing. It's just another variable. It works the same way. So I'm going to say 7u, this is just the power rule, to the 6th. Okay, that's dy over du. And then over here, I want to take the derivative of du, or well, I want to find du over dx. So in this case, I'm just going to use power rule again, and then a constant. The derivative of a constant is 0, using the sum rule. Employing a couple things here. This is just going to be 4. Okay, so we have these two things here. We have 7u to the 6th power times 4. Okay, now we can't just leave it with a u, because what we want to find is dy over dx. Remember, this is equal to dy over dx. Remember, we showed that earlier. So what we want is the change in y with respect to x, and that's not what we have here. We have it. Well, we kind of have some weird setup here where we have this one, and they're with respect to different things. So what we want to do now is recall that u equals 4x plus 3. So we can just plug this back in, and we can just say 4x plus 3 here to the 6th power times this 4. And this is just going to be equal to 28 to the 4x plus 3 to the 6th power. And that is the derivative, dy over dx. That is the derivative of this with respect to x. Okay, so if you wanted to, like I said, you could expand this out to your heart's content, and solve that on your own. Just use a bunch of other rules, and you'd get the same thing. But like I said, there's other examples. What about sine of 3x? Or what about sine of cosine of 4x squared? That's really, there's a lot in there. So you can actually use the chain rule a couple of times. This is an example. This is not an example of that. You can use the chain rule multiple times to find the derivative. And I will do this one in a moment. First, I want to do this top one here, just to show you can't always just expand it and use other rules. You have to use the chain rule in some situations. Okay, so same idea. We can split this into sine of u, and we can split this into 3x. Okay, so our first thing, find the derivative of this with respect to u. That's just going to be cosine of u. The derivative of sine is cosine, so cosine of u, times the derivative of this, which is just going to be 3. This is a pretty simple example. Plug the 3x in here. We're going to have cosine of 3x times 3 cosine 3x. Okay, not too bad. Another way, just if you're interested, if you write it in different ways, this can also be written as f prime of gx times g prime of x. That is also that's also a way you can write the chain rule, just using a different notation. So I think they both make sense. Go with whatever one you're used to, whatever you're taught to use. I think this one explains a little bit more on the g of x part on how I'm substituting that y in. For me, it's kind of implied because I've already worked with this. But if that makes more sense to you, then go ahead and just go by that. You don't have to worry about all these y's and u's and x's and all that. That might be a little bit confusing. Anyways, though, let's go to that really complicated one, right? Actually, I just deleted it, didn't I? Oh, well, it's gone now. Well, no, it's not. I can just slide over here. Okay. Okay, so let's take this one here. Let's bring it back over here. We're going to need the room for this. Okay, so what we have on the inside here is sine of cosine of 4x squared. And in order to do this, we're actually going to be breaking this into a handful of things, but the best way to do it, in my opinion, is let's start from the top. We need sine of cosine of 4x squared. Let's treat this as its own thing. So first, we're taking the derivative of sine here, cosine, and usually we would denote this by u. I'm just going to go ahead and write cosine. This is u, like this internal part is u, like we've done before. It's just a complicated u, cosine of 4x squared, right? And then we want to take the derivative of cosine of 4x squared and multiply it. And then you have to use the chain rule again. And so cosine of 4x squared is going to be negative sine. The derivative of cosine is negative sine. So negative sine of 4x squared. And then we multiply that by 4x squared, the derivative of 4x squared, which is going to be 8. I'm sorry, that is, 8. Yeah, 8x. Okay. So you'll notice I have 3 things here. And just know this itself right here is the derivative of cosine 4x squared. And this itself right here is the derivative of sine of this. Let me just write this. And this is f prime g of x. This is g prime of x. And you'll notice in order to take the derivative, we actually had to use the chain rule again inside of this. And you can do that. You might do that a lot. That may happen frequently, depending on what you're assigned to do. But that does happen quite a bit. And that's just about it for the chain rule. You may be wondering how I was able to cancel those u's, but not cancel them here. I guess one way to think about it is what I've been told is it's an operator, and you can't really do that with operators here. You can't just cancel these. If you did, from what I understand, it's just kind of forbidden. You're not really supposed to treat them like that. But if you did, it would still work. It would still be dy over dx. But I know in some situations that won't work. So just don't rely on that all the time. But it doesn't really matter here because it's the same idea anyways. You're still going to get your dy over dx, which is just a way of saying, confirming that it's true. But yeah, so just keep note to that. Keep that in the back of your head. Yeah, but that's about it for the chain rule. So if you have any questions, let me know, and I'll do my best to answer them. If you want more examples, or if you want me to explain the derivatives of cosine and sine and all the trig functions, I'd be happy to do that too. Just let me know, and I'll make a whole video on that. But it does take a little bit of time to make those because there's a lot of them and there's a lot that goes into them. So that'd be an exceptionally long video to make. But if you want it, let me know and I'll make one.